Now, it's great to be here today. My name is Cameron Cook. I'm an expert in computer vision, and I work for Airbus Commercial Aircraft in Toulouse. At Airbus Commercial Aircraft, I focus on how we can apply new technologies and new advances in computer vision to solving industrial problems. Now, to start off with, originally this talk was going to be called Into the Omniverse. However, then I later found out that Ekaterina, who gave a talk this morning from NVIDIA, was giving an Omniverse-shaped talk, and I was like, at the last minute, I had to change the title to Into the Metaverse. So I want to talk about a number of things today. Firstly, I want to talk a little bit about the context of Airbus, what Airbus does. I want to talk a little bit about computer vision, just to bring everyone up to a basic level. Then I want to talk about the challenges I'm trying to solve using artificial intelligence before finally leaving with a case study where I'll show you how we can apply synthetic data to solve a real-world problem. So setting the context. Airbus Commercial Aircraft is in the business of making aircraft. Now, on an average year, we make something on order of several hundred aircraft, so maybe 700, 800, 900 aircraft. And aircraft are made, all of the different components for the aircraft are made at factories all across Europe, and they're all brought together at our final assembly lines. Now, I really want to set some of the context for how large the scale of Airbus is. I don't actually know how many factories and plants we have, but I think it's about 40 to 50 all over the world, focused in Europe. We actually, I think, even have one for, I think we also have one for helicopters in Romania. So the A320 is our most popular aircraft. On a typical month, we make something like 50 to 60 of these aircraft, and we ship all the parts around to our final assembly lines, which are in the US. There's two in Europe, one in Toulouse, France, and one in Hamburg, and there's another one in Shenzhen in China. And all of the parts for the aircraft are flown around. The larger parts actually are so large they have to be flown around in a specialised fleet of aircraft. Well, we have 6 of these Beluga aircraft, which are specially designed, specially modified aircraft made by Airbus for Airbus to transport the fuselage, the wings, the other components of the aircraft around Europe from 11 different, I think there's 10 or 11 different places they fly. All these parts come together in a final assembly line. We've got one for the A350, which is a wide-body aircraft, another for the A330. And really, here you can see the scale of these operations when you can see the aircraft in the foreground. And here we've got one for the A380. We've stopped making the A380, but we're in the process of converting this final assembly line where all the parts come together into one for the A320, which is our small aircraft. If you've flown on an aircraft, more than likely you've flown on an A320. So if I can get this video to play, I'll quickly narrate it to explain what's happening. Building a commercial aircraft is actually a lot like building an IKEA set, in the seat like a bookshelf, where you've got all these different parts, you have to unpack them all, you have to bring them all together, and hopefully in the right order in the case of IKEA, but definitely in the right order in the case of a commercial airliner. Trust me, you don't want to have parts left over, that's generally not very good. Bring them all together and assemble the fuselage, which you can see here, but really this is the last 10% of how you build an aircraft, where all of the parts are coming together. And many of the parts we actually make within Airbus. So just pausing it here, because that's the end of the interesting stuff. Really, Airbus is a huge challenge. The last time I was in Romania was for Kodiak in 2019, and this was before COVID, which was a very different world. I'm sure we're all aware, things were quite different. And the challenge that Airbus had then was how quickly could we make aircraft. There's a huge demand for our customers for the aircraft we make, and that was that we couldn't make these aircraft fast enough. COVID's happened, we're in a different world now, but our customers still want aircraft. Everyone wants to travel again, and the future looks bright, and I'm an optimist, but we're also faced with the challenge of climate change. So not only do our customers want aircraft, they want more efficient, cleaner, greener aircraft. So in terms of, and these new, cleaner, greener aircraft, obviously they use a lot less fuel, which is great for the environment. And here you can see in terms of the actual volume of aircraft, we're being asked to produce like thousands and thousands and thousands of these aircraft over the next couple of years. But in fact, when you go forward about 20 years, we need to produce about 40,000 new aircraft. So it's a huge volume of aircraft we need to manufacture. Now, setting the context, what is computer vision? Computer vision is an incredible field. I've been studying it since I really started university, and I really started getting into it. And it's evolved all over the years. But fundamentally, computer vision is about how we can teach computers to see and understand the world. For humans, vision is our most important sense. It allows us to comprehend what's happening in the world around us, and we collect a huge amount of information. And I'm not a neuroscientist, so I'm not sure if this statistic is right, but I was reading somewhere that something like 80% of our brain, probably not 80%, is responsible for actually doing the processing for what we're seeing. Anyway, it's a huge amount of our brain is to do with actually understanding and perceiving the world around us. So in the case of computer vision as a human, in the case of a human, we can look at this image, and what do we see? We can very quickly and easily understand that there's an aircraft that's sitting on a runway, sitting on a taxiway. We can infer that it's probably about to turn onto the runway. We can infer it's probably about to take off. On the runway itself, we can recognize that it's a runway, and on the runway we can read there's 32L, which is the name of the runway. We can see where there's the grass, so we can see lots and lots of different things. So this is actually a task called semantic segmentation, where computers look at an image, and on a pixel-by-pixel basis, they work out what's what. What's the aircraft, what's the runway, what's the grass? There's also other information we can get out of the image. So for example, we could recognize the fact there's an aircraft and where it is. We could recognize the aircraft type. We could recognize the painting on the side of the aircraft and recognize that's a specific aircraft that belongs to Airbus. And we could also recognize the runway markings, all of these things. Now, what's been the catalyst for computer vision? Computer vision as a field's probably been around for 100 years. And when I say it's been around for 100 years, even before the advent of computers, mathematicians were studying how we could extract information from photographs. So you've got things like perspective, and they'd say, okay, we get a photograph and we can take measurements from it, and this field is called photogrammetry. But really the catalyst for modern computer vision was the advent of deep learning, which maybe happened 10 years ago. No, 8 years ago. It's a very, very, very short time frame. I think even TensorFlow, which some of you may have heard of, it's a very famous deep learning library, I think it's maybe 5 or 6 years old. The catalyst for deep learning was, firstly, the access to huge amounts of data sets. So there's a data set called ImageNet. I'm not sure exactly what year that came out, but that's less than 10 years old, I believe, as well as GPUs. So if you're here this morning, you would have heard from Ukraine, who was from NVIDIA, giving a talk. GPUs really have been the catalyst that's helped enable these deep learning models. They're hugely efficient processors which are incredibly powerful and are able to solve and to do the computation very, very efficiently for training these very powerful, very complex, very sophisticated artificial intelligence models. Now, I'm not sure from the audience how much everyone knows about machine learning and deep learning, but just to keep things super simple, I'll explain it in 30 seconds. There'll be lots of, I'll try and keep things simple. So basically, machine learning, deep learning. We've got an input data set, which is labeled. So what we mean by that, in the case of, we might be trying to train a classifier to tell the difference between a cat and a dog. So we've got lots of images with cats, lots of images with dogs. We tell the computer, here's a bunch of images with cats, here's a bunch of images with dogs. We've got a processor, like a GPU, which is specialized for deep learning. We've got an algorithm, a deep learning algorithm, which does the classification, and it's taught using this labeled data. This is a cat, this is a dog. So this works. This is historically how deep learning has worked, this is what's called supervised computer vision. This is how it's worked in 30 seconds. Now let's turn to computer vision at Airbus. At Airbus, we're using computer vision in lots of different areas. So what I focus on is mainly for manufacturing quality. but we also use computer vision for airline operations, for guiding aircraft. We're doing experiments with that, and also for processing documentation. Going into a little bit more detail, in the case of flight data, what I mean by this is that for future generations of aircraft, much like self-driving cars, we're trying to come up with algorithms that we can install on aircraft which will assist the pilots during landing. So at the moment, aircraft have auto-land, which uses GPS and specialised radio signals to guide the aircraft into land. But in the future, we're hoping that we'll be able to use computer vision to help augment these, much like self-driving cars. Also for airline operations, we're trying to see how we could put cameras on aircraft to help the aircraft understand when it's on the ground, what's happening around it. Things like, maybe the catering truck hasn't arrived, maybe the baggage wagon hasn't arrived, maybe the fuel truck hasn't arrived, to collect all this information for airlines. But really what I want to focus on today is manufacturing, where we're trying to use computer vision to help us make better aircraft, to make them faster, to ensure we've got the highest quality. And that's basically the two topics, is firstly the manufacturing process itself, but also quality. So working for Airbus, quality is paramount. There is nothing else that's important. Building an aircraft is hugely complex. Before I joked about building an IKEA set, where whenever I built a bookshelf or something like that, there's always parts left over. Obviously for an aircraft, that's not acceptable. So when we build an aircraft, we've got a rigorous process where everything is inspected to make sure that we're not missing anything and to make sure that there's nothing extra special, that there isn't anything that isn't meant to be there that's been left on the aircraft. Sorry, just give me one. Now, turning to the future. Airbus as a company, our customers are asking us for more customization. So what do I mean by this? When we make an aircraft, a lot of people think that's a bit like making a car, where, say, Ford, I'm not sure, Ford or Hyundai or Toyota, I'm not sure what the numbers are, but they probably make 10 million cars a year. Airbus makes somewhere on the order, let's say between, somewhere north of 500 aircraft a year. Now, the challenge for us is that each aircraft is special in its own way. When a customer orders an aircraft, they want an aircraft made to their specifications with their options. So really, we're a lot more like Rolls-Royce, where customers will come and they'll say, okay, I want that type of leather, I want these rims, I want this paint. So aircraft, it's very much the same, where airlines will say, okay, I want these seats, in the cockpit, I want to have this option. So for example, one option that we might offer is for the pilots, a USB charging port in the cockpit. This is something different where we need to run more wiring for that. They'll be different from any other aircraft. There's other airlines might want in-flight entertainment of one brand, which means some kind of wiring, or they might want satellite internet, which is more wiring in a different place. So very, very quickly, through customization, we end up with a situation where each of our aircraft is different, and when we're trying to do these inspections, this makes things very, very challenging, because it's not a case of we can just do a comparison to some, it's not like we just make one aircraft and we memorize what it's meant to look like, and then we check against that. Because each aircraft we make is unique in its own way. Another challenge that we have is building for the future. Obviously, climate change is a serious issue, and we're striving to build aircraft which are more fuel efficient and powered by new fuels like hydrogen and electricity. And building these new aircraft, they need to be lighter, they need to be stronger, they need to be made using new materials. So we need to come up with new manufacturing processes that just aren't possible at the moment. When you think about it, obviously we want to build the lightest, strongest aircraft possible so we can build a better aircraft than our competitor. So really the thing that's stopping us from building better aircraft is the limits of manufacturing technology. And one of the limits of manufacturing technology is how we can actually do inspections. Because there'll be a lot of spaces, for example, giving the example that when we make, say, the wing of the aircraft. At the moment, when we make the wing of the aircraft, we insert rivets into the surface of the skin. And what happens is that we need to be able to look at the other side of the rivet with a human to be able to validate and inspect them and make sure they're all perfect. But if we didn't need a human, then we could make lighter, thinner, stronger wings. So this is like one of the ways we're looking using computer vision. Another challenge is when we make aircraft, we want more and more data about the manufacturing process so that we can understand what went right and what went wrong. So we've got digital twins and digital mock-ups of the aircraft, but what we want to be able to do is we want to be able to populate these digital twins with information about every drill hole, about every rivet. Airbus drills 100 million holes a year, and I'm probably going to get the number wrong. Is it 10,000? I think it's 10,000 holes per aircraft, it's 10,000 holes per aircraft that we drill. So basically what we want to be able to do is to look at every single hole we drill. So if a drill bit starts going blunt and the holes it's drilling aren't as good as they could be, we know we can stop, we know we can change the drill bit. So really this is our aspiration, where we want to be able to build more sophisticated aircraft using more modern technologies, and we want to know more about our manufacturing process. Sorry, I think you can tell I'm pretty passionate about this, so I'm getting a little bit out of breath. But let's now let's turn to challenges. In manufacturing, computer vision has been around for a long time, and there's some situations where computer vision works fantastically and is really easy to implement. An example of this, I want you to imagine, is we've got an assembly line, if you've got some circuit boards coming down this assembly line. Let's say you're making the iPhone. I don't know how many iPhones they make a year, let's say 10 million, probably wrong, maybe it's 100 million, maybe it's a billion, maybe it's a million, I don't know. But let's say 10 million. They're all coming down the production line, they're all identical. You've got a camera set up on top, and basically, because you've got so much control of the situation, you control the lighting, they're all the same. All you need to do is take an image and then do a reference, do a comparison against what you see and what you know you should see. This is the dream I'd love to have. Unfortunately, this isn't the case. The challenge that we face are around reproducibility and coverage. So what do I mean by this? Basically, we're in a situation when we're building these aircraft. If every aircraft is different, then we can't just have a reference image for what we should see in a lot of cases. We also have the situation that when we're trying to capture data, aircraft aren't coming down a production line. They're hugely complex. They're made in different stages. They're made by workers. It's really artisanal. It's really, the comparison I make is it's really, it's like it's like when you imagine like Switzerland and you've got the people in the workshop making Swiss watches, or Ferrari, where you've got the people on their hands and knees doing the assembly by hand. It's really, really like that. So we have a lot of challenges around, when we're capturing data, like even if the people on the shop floor have a camera and they take a photo to do an inspection, there's really the question of what are we looking at, where are we? So there's all these different challenges. So going back to what I said about the production line is the state of the world we want. It's not the state of the world we have. The state of the world is something like this, where we've got people on the hands and knees inside the wing of an aircraft on the right, where they've got a torch and they're doing an inspection, or on the left, where you can see this is, I think it's the landing gear bay. So there's a maze of pipes, and it's all very, very complex. You've got people with torches looking around, looking for things. So it's incredibly complex to do an inspection. So these are the challenges that we face, where the dream for us would be to have some system where we could do a git diff against what we're meant to have and what we would like to have. So basically a git diff or a spell check or something like that, where we'd be able to systematically check for defects and anything that's out of order. We also need to do inspections not only in the manufacturing of the aircraft, but we need to do inspections on the cabin, the fuselage. So this is basically where all the passenger seats. If you've ever flown business class, I wish I had the money to fly business class. People have very, very high standards. It's very, very demanding. Everything has to be perfect. And when we're making an aircraft, it's much like if you were picking up your Ferrari. The leather seats would have to be perfect. So really, we've got this case where we're trying to automate all of these inspection processes to capture everything, to digitize it, and understand what's happening. Also, when we've got aircraft that are in service, what we'll often have is people going around this fuselage of the aircraft, Aircraft can fly through hailstorms, they can hit birds. The aircraft skin can be damaged, it can be dented, there can be lightning strikes. So really we've got to, at the moment it's it's very manually intensive where people will be out there with torches looking for issues. And to capture all this information about what's happening on the aircraft, there's lots of different ways it can be done. At the moment, we've got people with iPads, for example, where they'll take photos of the work they've done. We've done some experiments with cobots. So the cobot is a robot that can move around on the factory floor with a camera on it. We've also done experiments using drones with cameras, and the drone can fly around the aircraft and do an inspection. As well as this thing, which is my favorite, in the bottom middle, which actually sticks to the fuselage of the aircraft. It can drive around the aircraft, and it sticks to the aircraft like a slug or a snail somehow, using suction. I don't know how it works, but it's very, very cool. So there's all these different ways that we can acquire imagery. Going back to what I said before, Airbus operates at a huge scale. We collect data from, many different sources. It operates at a huge scale, huge manufacturing capacity. We're building lots of different things across the whole of Europe. So going back to the example I said with the iPhone, that's really the situation where we want. But we can never have that because we've got so much diversity in terms of what we're making. It's not just a case of we can train one computer vision model, and that computer vision model can solve all our problems. In reality, we probably have to train 10,000 different computer vision models. So this is what we want. We want, we want this production line, but in reality, what we have is the inside of an aircraft where someone's got a torch and they've taken a photo. But why do we want to do this? There's a huge number of different opportunities. Firstly, we can quantify for the first time defects. We can understand where they're occurring, how large they are. We can marry them back to our digital twins. So for example, let's say that, give an example, let's say that there's some part that goes from one factory to another, and we inspect the part when it arrives. We might find that there's always a dent on the lower left part of this piece of the aircraft whenever it arrives. And we might work out, okay, somehow it's being mishandled on the way from this factory to that one. So there's a lot of different opportunities to apply big data, to apply analytics, if only we had the data about how defects are occurring, how they're being, how parts of the aircraft are being damaged. So there's a lot of opportunities around the actual analysis. In terms of improvement, there's a few acronyms in here. So decrease rework. Basically, if we've got part of the aircraft that's being made and there's some issue, we have to do rework. So what I mean by that is the aircraft, when it leaves the factory, has to be perfect. So if anything is wrong, we have to fix the problem, which everyone hates rework. No one wants to, and it's like a problem where, let's say we're building an aircraft, or let's say, going back to the IKEA bookshelf example. The worst thing that can happen is you put together your bookshelf and you realize there's some critical part missing and the thing just doesn't fit together and just falls apart. When you try and push it together, it's no matter how hard you push, it all falls apart because you've realized you're on step number 17, and on step number 2, you forgot to put some part in. So when something goes wrong, we want to find out as soon as possible what's gone wrong. So we want to improve rates, that's basically making more aircraft, and we want to make sure that every aircraft we make is absolutely perfect so that our customers, the airlines who buy our aircraft, are as happy as possible. Also the people on the shop floor, we want to make them happy because we want them to be proactive, to be able to identify issues and take action. It's always embarrassing when, I make a mistake and then someone 2 weeks later says, hey, Cameron, you did some work in this factory and we shipped the part to another factory and then we found a problem and, ultimately you found out it's your fault. I'd rather have the spell check tell me that I've made a mistake and then I can fix on the spot rather than, my boss's boss telling me 2 weeks later. So really what we need to do is we need to be able to join the digital and analog worlds. So the real world of what's happening in the factory and then what's captured by cameras, and joining that with our digital twins, so our digital mock-ups of what's actually there on the shop floor. And to be able to do this, what we need to do is So in order to be able to join the digital world and the analog world, we need to solve a number of different problems using computer vision. We need to build a number of different models. We need to be able to build models which can detect, do semantic segmentation, so be able to detect things in image, to be able to split the image into different things, like you saw before, there was the aircraft, the runway, the grass. We also need to be able to work out where an image is taken from, so that we can work out what we should be seeing in an image, so that we can compare it to what actually is in the image. There's other things, so for example, let's say we detect a dent. We might want to be able to use computer vision to be able to estimate how large the dent is, and how deep the dent is. And then finally, robustness. When we're building these computer vision models, we need to be able to have faith that our models will work in practice and that we can trust them, because obviously we're in the aerospace industry, like trust is really important. We don't want things that kind of probably will work 95% of the time. We need things that really we can trust and really we can rely on. So now coming to the more technical part of the talk, why synthetic data? So before I mentioned that at Airbus we can't just build one model, we need to build 10,000 models. The problem is a lot of the time, to build 10,000 models, we'd need to build 10,000 labeled data sets. Now, I've annotated one or two labeled data sets. You've got a whole bunch of images and you sort them to cat, dog, things like that. If anyone here has done computer vision or deep learning, they know that doing this data curation, data annotation, data labeling is incredibly painful. I hate it, which is why I'm so interested in using synthetic data. So going back to just a very, very high level to explain very, very quickly when I say synthetic data. Instead of using real imagery, what we're trying to do is we're going to try and use rendering software to generate synthetic or fake scenes, and then what we're going to do is we're going to render those scenes so that we've got images that we can use to train our computer vision models. Very, very quick. So rendering can be incredibly powerful. We've got two images here where you can see that basically the scene you're seeing is completely fake, completely synthetic. And this is the kind of thing where maybe it'll take an hour to generate an image of this fidelity, but you can see it's visually indistinguishable. And if it's indistinguishable for us, it's also indistinguishable for our computer vision model. We have the ability to go and generate real data for anything of what it really should look like, what we really should be seeing. So going back to the example I said before, where we're trying to look for defects in the cabin, what we can do is we can generate a real image of what a perfect cabin would look like for that aircraft, for that type of aircraft. So then we could train a model to understand what defects could look like on that type of aircraft. So basically, we can do this. Building synthetic data allows us to train computer vision models for specific tasks, but also allows us to do a comparison between the virtual and the real. Maybe giving a more concrete example. Let's say that we've got a camera that's watching the factory, and we want to know where forklifts are. We want to understand where they are and where they're going. So one way we could solve this is we could get someone to watch hundreds of hours of CCTV and annotate exactly where the forklift is in each of those frames. Or what we could do is we could get a 3D model of a forklift, and we could generate a whole bunch of different renderings of the forklift in different positions. Now, when we do this, we're controlling absolutely everything. We're controlling the camera angle, we're controlling the lighting, we're controlling the position of the object. And because we're doing this and it's completely synthetic, when we generate the scene, we have access to a lot of information that we don't have in a photograph. So for example, we've got the RGB image, which is on the left, which is what we're going to feed into our deep learning model. But we also have a depth map. So basically, we've got information about how far each pixel is away from the camera. We've got a semantic segmentation map. So basically, we also know which object and what type of object each pixel in the image belongs to. So we already have all the training data we need. And this is the beauty of using synthetic data, is we can very quickly go away, generate the data we need for training a model, and then train a model. So this is incredibly powerful, especially if you hate labeling data. Very quickly, I'm going to talk about rendering in 30 seconds. Ray tracing is the most powerful method of generating images, the most realistic images possible. Basically what you do is you do a physical simulation of how light moves through the scene. It's pretty simple. For each pixel in the image, what you do is you trace a beam of light from that pixel out through the scene until it hits something, and then you follow and see where it goes. So at each point it hits something, what you do is you look at what the color of the thing it hit is. Now, you do this a whole bunch of times per pixel, and eventually you end up with a beautiful image that's very, very, very realistic. It's basically just a physics simulation. You need a bunch of different ingredients. Firstly, you need lighting, because obviously let there be light, you need light. You also need geometry for the objects in the scene. Objects in the scene have different materials. Some objects might be glass, they might be metallic, they might be shiny, they might be rough and diffuse. And then finally, you need a camera. So in terms of lighting, all these different ingredients are freely available. When we're training computer vision models, we want to make sure that they're robust to real-world environments. So one of the things which you can do is to use what are called environmental maps. Basically, what some people have done, very helpfully, is they've gone and captured the lighting from real-world environments, like this theatre, for example. And then they've made them public domain, open source, and available on the internet. So what you can do is every time you render your scene, you can use a different lighting map which represents the real world, so that your scene can have real-world, realistic lighting. You also need geometry and meshes for the different objects. In the case of Airbus, we have access to very intricate, very precise geometry of the aircraft because it's designed using CAD. So we can use this information for helping us to train our computer vision models. If you don't work for Airbus and don't have access to this CAD, to this data, and you want to train an object for some more real-world things, there's a great, I found out this afternoon, there's a great data set available from NVIDIA where they've made freely available to individuals a whole bunch of different assets which you can freely use. This is through the NVIDIA Omniverse. And you also need materials. So basically, as I mentioned before, different objects, different surfaces, the light interacts with them in different ways. You've got materials that could be shiny, metallic, glassy, glossy, whatever. Then you also need a rendering engine. The great news is that everything I've mentioned up to and including this point is either free or open source. So there's a lot of different rendering engines. The rendering engine is the software which actually does the simulation. At Airbus, we're currently doing experiments with a number of different engines, but my personal preference is one called Blender, which is free and open source. So we've got all of these different ingredients for generating realistic synthetic data. We've got materials, we've got our meshes, we've got our rendering engines, we've got our lighting. And the challenge is how you can bring these all together. And there's actually, the great news is that NVIDIA's developed this really interesting piece of software called Omniverse. Now, I'm not the right person to talk about this. We had the talk this morning by Karania, which is fantastic, talking about NVIDIA Omniverse, which is a suite of software or a library or an ecosystem of different software where you can plug in your modeling software, you can store all of your assets, and then use NVIDIA's renderer. So really what you're doing is you've got all of this representation of a scene in software, and then you're generating rendered images. Now at the moment, everything I've talked about has been what the state of the art is, where we are really at the moment, what concretely works really well. But still there's challenges around, okay, this sounds great, but how do we capture, the objects, the meshes to, train our models? Let's say, for example, that I wanted to train a computer vision model to detect this glass of water. There'll be the question of, okay, that's great, so I need to go away, I need to build the mesh of it, I need to get all the materials, I need to do all these things. That's pretty challenging. But the great thing is that at the moment there's some really exciting breakthroughs in technology. So for example, there's a new set of algorithms called NeRFs, which some of you may have heard of, which is basically where you can take a bunch of photos and you can generate a representation of a scene. And this really is as easy as capturing a whole bunch of different photos from different angles of an object. There's also other things where you can even go away, and maybe some people have heard about some algorithms called Stable Diffusion. So this is basically where you can describe a scene and you can get a representation of it. So there's lots of new algorithms, lots of new technologies, which really can be, which I think is really exciting to me in the future, that's really going to make it so much easier to be able to get the assets that you need to use synthetic data. Now, to finish up, I just want to do a case study on dent detection. So this is something we actually did at Airbus to solve a real-world problem. Now, the case study I mentioned was that when we've got aircraft are made of these fuselage sections, they're made of aluminium. And what happens is when the aircraft is in service, like I mentioned, you could have like hailstorms, or a truck could drive into the aircraft, or lots of different things can happen, and you end up with a dent in the aircraft. And what we wanted to do was to develop a drone system which could fly around the aircraft and look for dents on the surface of the aircraft using deep learning. So originally, when some people had this idea, they're like, okay, this is great. What we'll do is we'll get a section of fuselage we found lying out the back of Airbus. This is 100% the truth, which looks something like this, where they found some section of aircraft. And they're like, okay, let's get this, let's get this piece of aircraft, and well, we need to detect dents. So what we'll do is we'll go and deliberately dent this section of aircraft using hammers. So you have this section of aircraft, which is probably worth, I don't even know how much, €1 million, let's just say, where we've got one, it's for testing, but we only have one. So they went to put some dents in it, and there's maybe 10 dents in it. And they went away, they built their computer vision model for detecting dents. It works great. Now, if anyone knows anything about machine learning, you've got your test set, you've got your train set, you've got your validation set. And they went away and they put another dent in, and it didn't work great. It didn't work at all. So they've built this incredible model which can detect 1 of 10 different dents. At which point they're like, okay, we have a problem, because we had this single piece of fuselage which we put the dents in, and now obviously we need a lot more dents, and this is not scalable. We can't just get more pieces of aircraft to go and put dents in it. So that's when they came to me. And what we did was we used some open source software called Blender. Well, the first thing I said to them is like, this is a fantastic problem. This is a great case study. Clearly, it's ridiculous. You can't. This is a beautiful example of how we can use synthetic data. Now, the great thing is everything we did uses open source software, so you can follow along at home. Basically, we used open source software called Blender. Now, Blender is completely open source, and I love it because it's completely controllable through Python. So basically, we used Blender, and we used a tool called Blender CLI rendering, control line interface rendering, where basically what you can do is you can write Python scripts that can define scenes and then render them. So in this case, what you can see is a scene. You can see there's a dent. It's a bit hard to see here on the left, but you can, actually it's very, very hard to see. But basically, we've got a scene, we've got a dent. Actually, I think maybe you can see there in the orange. There's a dent in the surface, and we can configure different dents in the surface of the aircraft programmatically. Then we can define different materials. So for example, what we can do is we can say, okay, what if the surface of the aircraft is glossy, what if it's less glossy, what if it's more faded, what if it's this color, what if it's that color. So we can go away, we can define all of these things programmatically, and we can generate incredibly realistic synthetic images. The drone actually has a laser on the front of it which scans a line onto the surface of the aircraft, so that line deforms when there's a dent, and here you can't even see as a human, but there's basically a dent there. And the great thing is that when we generate all of this, we get the metadata for where the dent is, how large it was, generated for free by the software. So in about an hour, we can go away and generate 10,000 different images of the surface of the aircraft. And honestly, if I was going to do some annotation, I'd probably annotate 10 images in an hour because I'd probably get bored after the first 5 minutes and go and have coffee. But with the software, it can sit there, go away, churn out 10,000 images, and we end up in a situation where we've trained completely on synthetic data, validated on our real-world data, which was the aircraft section we've dented, 100% precision, 100% recall on a sample size of 11, but still very, very happy. Now, one final note. The reason why I love synthetic data so much is that it's incredibly powerful. Last year, as I mentioned before, we're trying to come up with systems that we can put in aircraft that can help improve the safety of flight, especially with landing. Now, last year, something completely crazy happened, and people swear this happened. I've tried to find actual information or actual photos to be sure this happened, but allegedly in India, there's a situation where some elephants got onto the runway of the airport. And these aren't real photos. I just went to Stable Diffusion and typed in, photos of elephants on runway in India, just to have for the presentation. So these are completely synthetic images. But the beauty of synthetic data is even when there's something completely absurd that you may never have in your training data set, you may never have seen before, if you can imagine it, you can generate it so that your model can see it, so that you can understand, okay, even if there's something that's as absurd as an elephant on the runway, pretty crazy, we know that our algorithm will work in that situation. So just to finish up, synthetic data is incredibly powerful because it's very cheap, very easy. You don't need to pay any money. It's really only what you can imagine is what you can do with it. And that's why I love it so much. And thank you so much for all of you guys. It's all of you here. It's been fantastic to have you here. And I open the floor to questions.